want to take a moment to go over the min and max problems we did in class, just to make sure you know how to solve them in case you have a min and max word problem on your test coming up, which is decently likely. So let's go ahead and talk about all three of these. The first one of these is probably the most challenging one. Part of that is the statement of the problem. So it says there's an isosceles triangle where two rectangles are inscribed. It says many others could also be inscribed. What are the dimensions of the inscribed rectangle having the largest possible area? So it's a little unclear what this is saying, but what it's saying is if you have an isosceles triangle, you can inscribe a rectangle a lot of different ways. Inscribing a rectangle means all the vertices of the rectangle are on the sides of the triangle. So something like that could be it. It could be something like that. There are a lot of different ways you could inscribe it. We're only going to do one of those, and we'll end up finding what dimensions give us the largest area of that rectangle. So there's really only one rectangle here. Let's go ahead and draw that here. With these diagrams, sometimes the bigger you draw it, the better. So this whole side is 15. This whole side is 15. And this bottom side is 18. All right, and then I'm going to go ahead and draw my rectangle. Again, inscribed, which means all the vertices of the rectangle are on the triangle. So maybe something like that. And I'm going to go ahead and call the sides of my rectangle x and y. Because again, we're trying to find what will give us the largest possible area of the rectangle. So let's write what that is. The area of the rectangle is x times y. The problem is I can't find the maximum of that right now because it's a function of two variables. If it's a function of a single variable, I can either use the vertex formula if it's quadratic, or I can graph it if it's higher than that and find that maximum. But with two variables, that's not something I'm able to do. So I need to somehow get a relationship between x and y, and that's kind of what makes this problem a little bit more difficult. So here's what I'm going to do. A little bit of geometry. The first thing is I'm going to drop an altitude in this triangle from that vertex angle down to the base. Now from geometry, when you drop an altitude to the base from an isosceles triangle, the vertex angle of an isosceles triangle to the base, it bisects the opposite side. So this would be 9, this would be 9. And because of symmetry, that rectangle on the bottom has a total length of y, but it's going to bisect that. This will be y over 2, this will be y over 2, or 1/2 y each. Again, because that altitude bisects the opposite side, if it's an isosceles triangle or equilateral. So now that we have that, what I'm going to look at is kind of just the left half of the triangle for the rest of this problem. I'm just going to look at this piece right here, like that. All right, so let me draw that over here, where I have a little bit more room. Okay, so that's a right triangle. I know that this is 9, I know that this is 15. If I want to find the missing side, b, I can use the Pythagorean theorem. 9 squared plus b squared equals 15 squared. Or it's a Pythagorean triple. And what you'll find is that missing side is 12. Okay, what we also have, if we look back at the original, is again, we know that this whole half of the triangle is 9. This half of the square is y over 2. So this little piece right here is the remainder, 9 minus y over 2. It's what's left over. Now I want to go ahead and draw that in my picture here. So I've got the large right triangle, the half of that isosceles triangle, and then it looks like I've got another triangle here, another right triangle that has side lengths of x and y over 2. All right, so what can I do with this? Well, notice that these two triangles, this small one that I just drew and the larger one, are what are called similar triangles from geometry. Okay, so first of all, how do I know they're similar triangles? There were a few different ways of showing two triangles were similar, but the most common way you probably used was angle-angle similarity, which says if you can find two pairs of congruent angles in two triangles, then the triangles have to be similar. So notice that, for starters, they both have a right angle. there's one pair. And then they also both share this angle right here. Right? The large angle or the large triangle and the small triangle both share that angle. So there are two pairs of angles that are congruent in both triangles. So these two triangles are similar. Now, what similar triangles allows you to do is to set up a proportion. And there's a lot of different ways you can set it up. But basically the way I do it is I say like the short side over the long side equals the short side over the long side. Or you can flip those. There's a lot of different ways you can do it. So for example, looking at this, if I look at the vertical legs of these triangles, the short side, x, over the long side, 12, equals, all right, let's look at the horizontal legs of these triangles. So notice this piece is y over 2. In the large triangle, the whole thing is 9. So that's a relationship that I can use. Oh, sorry, actually, this was 9 minus y over 2. I didn't copy that over correctly. This piece right here is 9 minus y over 2. Right, we said that over here. So 9 minus y over 2 over 9, the short over the long. If I cross multiply, I get 9x equals 108 minus 6y. And I'm just going to divide by 9 because it seems easier to solve for x. So dividing by 9 gives me x equals 12 minus 2/3 y. So finally, there's the relationship between x and y that we were looking for. If we think back to what we were doing, we were trying to maximize the area, but it was two variables. Now I have a relationship between x and y. I can plug that expression for x in, and I get that the area as a function of y alone is y times 12 minus 2/3 y. I just swapped the order of the multiplication there to make it look more natural. If I distribute the y through the parentheses, I get that the area in terms of y is negative 2/3 y squared plus 12y, which is a quadratic, so I can use the vertex formula to find the coordinates where the maximum are, or maximum is. So, remember the vertex formula is usually x equals negative b over 2a. In this case, the way this function is written, the independent variable is y, so I'm going to say y equals negative b over 2a, negative 12 over 2 times negative 2/3. That's negative 12 over negative 4/3. The negatives cancel, I get 12 times 3/4, which is 9. So the value of y that's going to maximize that area is 9. If I want to get what x is, plug it in that relationship between x and y. X would have to be 12 minus 2/3 of 9. It's 12 minus 6, which is 6. So to answer the question, what are the dimensions of the inscribed rectangle that have the largest area? Remember, the dimensions of the rectangle were x by y. So I would say a 6 by 9 rectangle would give us the biggest possible area of that rectangle. Or if it asked, what is the maximum area, you would say 54, because it's length times width, 6 times 9. Number 2 has this rectangular piece of cardboard, kind of like a problem we did in class, but with a little difference to it. This rectangular piece of cardboard with a perimeter of 30 inches. So let's draw it maybe like this. But it has two parallel and equally spaced creases. So maybe something like this and like that. So if you remember the one we did in class, we folded it up with 3 creases. We folded it up to make a square prism. So you might be able to imagine that, well, if I'm only making 2 creases, that's going to be 1 less edge in the bases. So it's actually going to form a triangular prism. So it's going to look something like this. Triangular prism, like this. And again, if you have a piece of paper at home, you're welcome to kind of try it on your own and verify that, but it would be a triangular prism. Okay, so the cardboard is then folded to make a prism with open ends that are equilateral triangles. So it goes ahead and tells you that. So just like we did in class, I think it's easiest if maybe we call these pieces x, and then we can get expressions for the other sides. Okay, well, the perimeter is 30, So far, of my 30 inches that I'm allowed, I've used 6x. So I have 30 minus 6x left to split evenly between both sides. So if I have 30 minus 6x total, divided by 2, gives me 15 minus 3x. That will be each of these sides. And if you add up all those sides, you will certainly find that the perimeter is 30 inches. All right, so looking at this problem then, looking at how it's going to unfold into or fold up into this three-dimensional shape, notice that these are going to be your x and x and x. The length, or technically the height of this prism, is going to be 15 minus 3x. So in part A, we want to show that the volume is v of x equals that. So I'm going to do that down here. So the volume of a prism with any shape base in general is the area of the base times the height, where again, that h represents the distance between the bases. That's, in this case, 15 minus 3x. B is the area of the base. And there is a formula for the area of an equilateral triangle, but not everybody knows it. So what I'm going to do instead is I'm going to redraw the base a little bit bigger. Again, all those side lengths are x. I'm going to drop an altitude because for the area of the base, that triangle, I'm going to use 1/2 base times height. So those are each x. If I drop an altitude, just like we saw in the last problem, it's going to bisect this side, the opposite side. It is also going to bisect the angle at the top. And if you remember, in an equilateral triangle, all the angles are 60 degrees. It's going to bisect it into 30-degree angles, which forms two 30, 60, 90 triangles. If you didn't know it formed 30, 60, 90 triangles, you can still use the Pythagorean theorem to find that height of the base. But I'm going to use 30, 60, 90s because we will want to use those later this year. So remember, in a 30, 60, 90 triangle, the sides are in a ratio of L to L root 3 to 2L. So notice here, the one opposite the 30, that's L, so x over 2. So opposite the 60, I'd have x over 2 root 3. And opposite the 90, I would have 2 times x over 2, or x, so it matches up. So that is the height of the base, not to be confused with the height of the prism. All right, so the volume is the area of the base, 1/2 base times height, times the height of the prism, 15 minus 3x. We can see that again in the picture up here. If I simplify that, I get v as a function of x is, okay, so in the denominator I only have a 4. The numerator, x squared root 3, so root 3 over 4x squared, sure enough, times that 15 minus 3x. And that's my volume as a function of x. Okay, so for part B, it asks, what is the domain of V? So remember, for the domain, we need all the dimensions to be strictly positive. So when I look at this, I can say, all right, well, looking at the original, I would need x to be positive. I would need 15 minus 3x to be positive. Those are kind of the two dimensions that I see in that big prism. You could also check that we need that the height of the base, x root 3 over 2, to be positive, but it turns out it's the same as x just being positive. So I need x to be positive. I need 15 minus 3x to be positive. All right, that's already taken care of. Here, if I move the 3x over and divide, I get that x has to be less than 5. So putting those together, if x has to be greater than 0 and less than 5, my domain would be x is between 0 and 5, or 0 less than x less than 5, just like that. So then for part C, the last thing we want to do is we want to put this in our calculator and find the maximum volume. So let's go ahead and take a look at that. If I bring up my calculator, when I create a new document, a graphs page, you can kind of stop and rewind if you need to, if I'm going too fast. I'm going to put in the volume formula they gave me. So that was control divide to get a fraction. So square root of 3 over 4 x squared times parentheses 15 minus 3x. That's the volume formula we got from part A. So if I type that in, hit enter, I get what looks like a cubic, but it's hard to see where that maximum is. So we're going to use Mr. Smith's secret recipe for getting a perfect graph. Remember the two steps: you do menu, window zoom, window settings, adjust it to the domain for this problem. So I'm going to say 0 to 5, leave the y's alone for now. So that looks a little bit better. We can see where the x's are. We just need to zoom out the y's now. So the second step is menu, window zoom, zoom fit, just about almost always works. So I'm going to select that. And we get a beautiful looking graph right there that we can find the maximum of without too much trouble. So then remember, to find the maximum, I go menu, analyze graph, maximum is option 3. Okay, go a little bit to the left of that point, hit enter. Go a little bit to the right of that point, hit enter. And there's your maximum. Now remember, if you want more decimals, you can hover over each of those using your trackpad and hit the plus button. This will be fine for me right now, so I'll just write what I have down here. So 3.33 and 24.1. So to answer the question, find the value of x. That was about 3.33 inches. And give the approximate maximum volume. The max volume was that y value, 24.1 cubic inches or so. So remember, v of x, the input is x, which is that how far apart you're creasing it, and the output of that function is v, the volume. It's the y value. So keep that in mind. For this last problem, another bit of geometry here and there. A cone is inscribed in a sphere of radius 6, as shown below. Express the volume of the cone as a function of x, using 1/3 pi r squared h. Then give the domain of this function. All right, so the big thing here to notice is that the radius of the sphere is not the same as the radius of the cone. Okay, if you look, here's the center of the sphere. This goes to the edge of the sphere, so the radius of the sphere is equal to 6. We do not currently know the radius of the cone. The radius of the cone would be this green segment right here. We don't know that. I'm just going to call that r. But if I complete this very colorful triangle, at the bottom, notice this is a right triangle. The height of a cone is going to be perpendicular to its radius. We have a right triangle, and I can use Pythagorean theorem to get the radius of the cone, r, in terms of x. Okay, so r squared plus x squared equals 6 squared. That gives me r squared plus x squared equals 36. If I solve for r, remember I'm not solving for x here, I'm trying to get what the radius is. If I solve for r, I get that r squared is 36 minus x squared. If I square root both sides, usually from last year you know that when you square root both sides, you need a plus or minus on the radical, but in this case, we don't want a negative radical because the radius should be a positive quantity. So I can ignore the negative. And I get that that's my radius of the cone, not of the sphere. This is my radius of the sphere. So using this volume formula, the volume as a function of x is 1/3 pi r squared. Remember, doing the volume of the cone. So the radius of the cone is the square root of 36 minus x squared, right, pi r squared, times h. The height of the entire cone, here in green, is x plus 6. You could simplify that a little bit. 1/3 pi, when you square a square root, that's just going to undo each other. So 36 minus x squared times x plus 6. So that is the volume of your cone as a function of x. Now, as far as the domain goes, the way that I would think about it is we need all of these dimensions to be strictly positive. So to do this, I would look at, first of all, we have that measurement x in the cone. We know that x has to be greater than 0. You could say x plus 6 has to be greater than 0 as well, but that'll end up being redundant. So I'm just going to say x has to be greater than 0. Still part of part A, sorry about that. And also we need that radius to be positive. We need the square root of 36 minus x squared to be positive as well. In particular, kind of looking at this function here, we need 36 minus x squared to be positive. Now to solve this, we haven't technically talked about this year. You could do a sign analysis, but I think the easiest way to solve this is maybe just kind of think intuitively. If I want that to be positive, maybe move the x squared to the other side. This isn't really the way we want to do this most times, but we're going to kind of use some intuition to figure it out. If I want x squared to be less than 36, I want to pick values of x that are less than 6 in absolute value, right? 6 squared is 36. Anything bigger than 6 that I plug in for x is going to be greater than 36. Same thing for anything less than negative 6. So technically I want values of x between negative 6 and positive 6, but because x can't be negative, right, because of that, I'm just going to say x has to be less than 6. So we kind of thought about it just using our number sense a little bit. So our domain would be 0 less than x less than 6. So then finally for part B, if we graph this, go over to the graphing calculator, we can get the value of x that maximizes the volume and the maximum volume itself. I'm going to go ahead and just get a new document. It's usually easier to just do that. Let's go ahead and graph this. So remember, it was control divide to get a fraction, 1/3 pi, just down here, times parentheses 36 minus x squared times parentheses x plus 6. Okay, that's the function that we saw. So now if I hit enter, I can see it looks like a cubic. It's rising on the left, falling on the right. So I need to do my kind of magic formula for making it look good. Menu 4,1. Adjust the x's to the domain, so 0, 6. Then go ahead and zoom fit. Menu 4A to zoom fit. We can see what this graph looks like. So it looks like we have our maximum point up there. Okay, we have our maximum point right up there. So let's go ahead and see what that is. Menu, in this case, analyze graph, maximum, go a little bit to the left, hit enter, a little bit to the right, hit enter, and we can see 2,268. Again, I won't bother getting more decimals, but you can if you want. So if I fill that in, the value of x that gives you the maximum volume is about 2, maybe exactly 2, who knows. And then the maximum volume, I'm pretty sure this one has decimal pieces to it. The maximum volume is approximately 268 units, right? It doesn't have any units with it, so we'll just say 268. So hopefully as I went over those 3 problems, it made it a little bit clearer on what to do. You may not have anything quite as difficult as these on your test, but you do need to kind of think a little bit outside the box here and there and be comfortable with that as we go through the course this year.